welcome back. Today we're going to be continuing our journey through integration and then focus on some applications in the realm of continuous probability theory. So in case you don't know any probability theory, generally speaking in short, the probability of an event is the likelihood of that event happening, where that likelihood is expressed as a number between 0 and 1. Where 1 is in some sense telling you that it's guaranteed to happen, and if the probability is equal to 0, that it guarantees that it's very unlikely or practically impossible to happen, depending on what type of 0 you are using. But all those things are firmly defined in the realm of probability theory. Here we're just going to give you a general exposure to the concept of probability and how you can use integrals for generating such quantities. So to start, let's assume that x is a continuous random variable. For example, temperature, time, density, velocity, or anything that doesn't have any discrete characterizations. For example, the number of cats that you have in your home, the number of cups of water that you drink in a particular day, assuming that you can't have fractional cups, how many people visit a restaurant to eat for lunch, and so on. So we have continuous versus discrete random variables, so our conversation today is only focused on continuous. Then the function little f of our random variable x is said to be a probability density function, or PDF for short, if that function satisfies two properties. The first property is that that probability density function must always be greater than or equal to 0 for all x in its domain, and the integral from minus infinity to infinity or across this domain must be entirely equal to 1. This second property in some sense guarantees that the area under the curves of probability density functions correspond to probability measures. And in some sense, the probability that you have anywhere from minus infinity to infinity gallons of water in your home is guaranteed to be 1 because it covers the entire span. And the requirement that the density function be negative is so that you don't have any negative probabilities. So the total amount of area is 1, and all of the areas must be positive and not negative, right? So that's pretty much what's going on with these two definitions. Now, let's introduce a particular type of continuous random variable that is sometimes referred to as an exponential random variable. So we say that a random variable that is continuous, x, is said to be exponential if it has a particular probability density function that follows an exponential decay curve, where lambda is just some rate parameter for our density function, and the domain of this density function is all x greater than 0. So what exactly does this probability density function, or potential probability density function, because we haven't verified that, what does it actually look like? Well, lambda is assumed to be a positive number, and exponentials are always non-negative functions. So what we're going to have is a function that follows, again, this exponential decay curve, right? So is this really a probability density function? Well, it has to satisfy two properties. In particular, f of x must be greater than or equal to 0 for all x on its domain, and in this case the domain is 0 to infinity, and is indeed always positive. And the second property is that the entire area under this curve must be equal to 1. So does the area under this curve really equal to 1? Because it covers an infinite region, so it's possible that it's not even finite. And does this lambda have anything to do with that area? I mean, if you make lambda bigger, does the area get bigger? Or does it always stay 1 regardless of the value of lambda? Because if it doesn't really matter, then in some sense the exponential distribution is not just a distribution, but more so a family. So let's see if the area under this potential PDF is actually equal to 1. So the integral from 0 to infinity of lambda e to the minus lambda x, and let's assume that lambda is just an arbitrary positive constant, and see if the family of distributions is equal to a family of probability density functions. So lambda is just a number, so I'm going to be factoring that out. So I'm going to have lambda times the integral from 0 to infinity of e to the minus lambda x dx. Lambda is, again, just a number, so minus lambda is also a number. So I can just use some inverse chain rule here, and I'm going to have lambda times minus 1 over lambda times e to the minus lambda x, and then we're going to be evaluating this as x goes to infinity and as x goes to 0. Again, notice that as x gets close to infinity, e to the minus lambda x gets arbitrarily negative because lambda is a positive number. So e to the minus infinity is going to be equal to or going to 0 in the limit. So that means this is going to be equal to what? So notice that these constants cancel to minus 1, and we're going to be left with 0 minus 1, which is going to be equal to 1. So what exactly does this mean? So that means f of x is a PDF for our random variable x, and in particular is true for all lambda greater than 0. Before going into a practical example of the exponential distribution, I want to first talk about the mean of a continuous random variable. So the mean, or average, of a continuous random variable is defined by another integral over the entire domain of your function, from minus infinity to infinity generally speaking, of the product of x and your probability density function. I won't dive into sort of where this formula comes from and why we define this as the mean. But if you know anything about statistics, it does generate in Simpson's, in terms of motivation, from cumulative probability density functions and frequency distributions where you have a lot of repetition. So what exactly is the mean of an exponential random variable, and what exactly does that even mean? Because notice that we have this lambda rate parameter, but we don't really know what lambda represents. So maybe finding the mean will help us get some intuition as to what that lambda is going to represent in terms of real-world problems. So the mean of an exponential random variable will be equal to the integral from 0 to infinity of x times our probability density function. As usual, lambda is a constant, so I can factor that out. So I'm going to have lambda times the integral from 0 to infinity of x e to the minus lambda x dx. And now I have this integral with x and e to the minus x. So what I want to do is use integration by parts to solve for this integral. I'm going to be letting my u be x and my dv be everything else. So if u is equal to x, then du will be equal to dx. If I choose dv to be equal to e to the minus lambda x dx, then v will be equal to minus 1 over lambda e to the minus lambda x. Right? So this sets us up for some nice integration by parts. So this is going to give us what? So lambda times, so uv, and keep in mind we still need to apply our limits, minus the integral of v du. Right? So a couple things here. Notice that those minus signs will make a plus that 1 over lambda can factor out. As x gets close to positive infinity, this term is going to go to 0. And as x gets close to 0, this term is going to get close to 0. So when we subtract 0 minus 0, this entire term is going to get close to 0. So we're just going to be left with lambda times 0 plus 1 over lambda. So 1 over lambda times the integral from 0 to infinity of e to the minus lambda x dx. So once I have this, then I can distribute my lambda inside, and those lambdas will cancel. So we're just left with the integral from 0 to infinity of e to the minus lambda x dx. So this integral is actually quite nice. So it's going to be minus 1 over lambda times e to the minus lambda x, and then we just need to evaluate our limits. So x to the infinity, x to the 0. And that's going to give us minus 1 over lambda. So it's going to go to 0 minus 1. That minus 1 changes that negative to a positive, so we're just left with minus lambda. So this is the mean of an exponential random variable. So let's sort of summarize that formula here and interpret as usual. So therefore, the mean for exponential is 1 over lambda. So if somebody asks you, well, what exactly does lambda represent, we can solve this equation for lambda, and we say that lambda is equal to the reciprocal of the mean. So if the amount of time that you spend shopping in a grocery store is exponentially distributed, and on average people spend about 35 minutes in the grocery store, then the rate parameter for that distribution will just be 1 divided by that average, 1 divided by 35 minutes. Right? So now we have some interpretations of what this lambda even represents. Before I get into an actual practical example, I just want to mention just a couple other metrics that are used in probability and statistics. The first one is called the second moment of a continuous random variable, which some people will abbreviate by mu x squared, which can be found by doing the integral from minus infinity to infinity of x squared times the probability density function. And another one is called the variance of a random variable, which some people will abbreviate by sigma squared of x. And this is found by doing the second moment minus the mean of x squared. And one can find that for exponential random variables, the second moment will be equal to 2 over lambda squared, and the variance will be equal to 1 over lambda squared. So those are some little algebraic calculations that you can practice on your own. And also do note that sometimes people will use a different notation for the mean. You may see them write e of x, which stands for the expected value, and similarly mu x squared will sometimes be denoted as ex squared, and sometimes the variance will be represented as varx, and hence varx is equivalent to ex squared minus e of x, the quantity squared. Won't be getting into the interpretation of second moment and variance, but feel free to check out my variance and probability sequence to sort of learn more about that. Now let's get into a practical example of the exponential distribution and how we can use integrals to solve them. Let's assume that the amount of time that people spend on one math problem is exponentially distributed with a mean of 12 seconds. And let's assume that we select one person from this population. For that person that we've selected, what is the probability that the amount of time, and let's assume that the amount of time is denoted by random variable x, is more than 20 seconds for one math problem? So this is going to be equal to what? So what is the likelihood that they spend more than 20 seconds when the average is equal to 12? So what this is going to be the integral from 20 to infinity of our probability density function lambda e to the minus lambda x dx. In terms of its picture, we're assuming that this amount of time that we spend on one math problem is exponentially distributed, so the likelihood that we'll spend more than 20 is just this area here, which is why we're using an integral to evaluate that. So since the average is 12 seconds, that means the lambda rate parameter is just going to be equal to 1 over 12, or 1 over 12 seconds. So I'm just going to keep it as lambda for now until I actually need to evaluate that. So this is going to be equal to what? So this is going to be equal to lambda times negative 1 over lambda, and then we're going to send x to infinity, and then send x to 20, and then evaluate that. So as usual, this lambda minus 1 over lambda will cancel into a minus 1, and then we're going to have 0. Oh, where'd my e to the minus lambda x go? So we're going to have 0, and then minus e to the minus 20 lambda. So once we simplify that, that's just going to be equal to e to the minus 20 lambda. But e to the minus 20 lambda in our problem is the same as e to the minus 20 divided by 12. And one can find that's approximately equal to 0.1889. So the probability that one person spends more than 20 seconds on a math problem is about somewhere around 19%. Let's look at a couple more variations of this problem. What is the probability that they spend at most 5 seconds? So similarly, this is going to be equal to the integral from 0 to 5 of our probability density function, which is going to be equal to, if we apply, basic ideas, so what exactly is less than 5? So less than 5 is going to be equal to this area here. So that's the probability that x is less than or equal to 5. What about the area to the right of that point? What is this area? Well, that would be the probability that x is at least or more than 5 in the continuous realm. And one can verify that in the continuous realm that greater than, equal to, or equal probabilities, at least up to some infinitesimal distance. So we can actually already solve these types of problems. So maybe we can just use complements to solve this problem just to save some work. So this is going to be equal to 1 minus the integral from 5 to infinity of lambda e to the minus lambda x dx. And then we can just use the same structure as we did before because the only thing we changed was lambda here. So that's going to be 1 minus e to the minus 5 over 12. And one can find that's approximately equal to 0.3408. Right? Now let's assume that we have the area, or the probability that our values are between two finite values that are non-zero. So what's the probability that they spend anywhere from 10 to 15 seconds, right? So let's draw our little picture. So now we're going from 10 to 15, and what we're doing is we're aiming for this area here. So what we can do is we can find the area to the right of 10, we can find the area to the right of 15, and then subtract. So we can write this as the integral from 10 to infinity of our density function, and then minus the integral from 15 to infinity of our density function. Or you could do the integral from 0 to 15 and subtract the integral from 0 to 10. You should get the same exact area in either case, right? So regardless of the approach you do, you're going to have what? You're going to have the e to the minus 10 over 12 minus e to the minus 15 over 12. Once you work out that math, you're going to have that's approximately equal to 14.81%. And that's how you can do probabilities with exponential random variables. The last thing that I want to introduce today is another distribution that follows continuous random variables and is also related to exponential random variables. So what we're going to do is we're going to begin with a sequence of random variables x1, x2 down to xr, where r is a natural number assumed to be bigger than or equal to 1. And let's assume that all of them are exponential random variables. And let's assume that each of them are independent of each other, where the likelihood of one happening does not affect the likelihood of the other taking a particular value. And let's assume that each of those exponential random variables have the same exact mean, i.e. or equivalently the same exact rate parameter, lambda. And now let's define a new random variable to be the sum of those independent and identically distributed exponential random variables. Then, by definition, the distribution of x is said to be a gamma distribution, and one can find that the gamma probability density function is going to be equal to this structure here. Lambda to the power of r, so the rate parameter for each of the individuals, to the power of the number of exponential random variables we have, divided by r minus 1 factorial times x to the r minus 1, and then times e to the minus lambda x, right? The proof of this is definitely beyond the scope of this course, but with a little bit of probability theory, it is definitely possible. Being able to prove that the area underneath of this probability density function being equal to 1 also is not tremendously complicated, but you need a little bit of clever work and clever manipulations in order to figure that one out, but we'll eventually get there if we haven't already. And showing that the mean of this exponential sum, aka gamma, random variable, being equal to r over lambda is actually not too difficult as well. Intuitively speaking, for the mean of a gamma random variable, it's actually not too bad if you know properties of expected values from statistics. If you do, let me briefly entertain you with what that looks like, because pretty much what we have here is the expected value of the sum of exponential random variables. And one can show that since in some sense exponentials are linear operators, or expected values are linear operators, then what we have here is the expected value of x1, x2, all the way down to the expected value of xr. And since each of them have the same exact rate parameter, lambda, that means each of them have the same exact mean. So that means this is 1 over lambda, this is 1 over lambda, all the way out to 1 over lambda, and that's r over lambda since we have r of them. So the proof of that actually isn't quite hard as long as you have properties of expected values behind you. Now, what exactly does this gamma distribution look like? Well, the gamma distribution does not look like the exponential distribution for r bigger than 1. It actually has this particular shape. And by property 2, this area from 0 to infinity is equal to 1. Now, how can we actually calculate the area underneath this particular probability density function between two non-trivial values, like from 5 to 10 or 100 to 150? That is not too easy, right? But keep in mind we do have approximations for all of these things in the special case where we actually can't get the exact values. So let's take a look at how we can actually use the gamma distribution to solve some real-life problems. Let's revisit the same problem as before, and let's again select one person from this population. What is the probability that it takes anywhere from a minute to a minute 20 seconds to cumulatively spend on 7 independent math problems? So here what we're looking at, again, is a sum of exponential random variables. So x1 is the first math problem, x2 is the second math problem, all the way out to the 7th math problem, and we're looking at the cumulative time that it takes for all of them. So we already know, since we're assuming that each math problem is independent of the other, and since each of them are the same exact exponential random variable, each with 12 seconds average, then this random variable, this is going to be a gamma random variable. So what we are interested in finding is the probability that it takes anywhere from a minute to a minute 20 seconds. So that's going to be 60 seconds to 80 seconds, and we're interested in finding the area between 60 and 80 for this probability density function. So since we do not know how to integrate this gamma distribution, what we can do is we can use some approximation methods that we learned earlier. So let's consider this interval 60 to 80, which is a pretty wide interval, and let's assume that we're going to approach it with 4 subintervals. So that means our midpoint of 60 and 80 will be 70, and then we're going to have 65 here, we're going to have 75 here, and then we also need our midpoints for our midpoint method. So this is going to be equal to 62.5, 67.5, 72.5, and 77.5. So if you just use left endpoint rectangles and right endpoint rectangles, 4 is definitely not going to give you a pretty accurate answer. So if we go ahead and calculate, for example, the left endpoint rectangles, which are going to be based on 60, 65, 70, and 75 with the equal spacing of size 5, you can find that this approximation is approximately equal to 0.2592. If you do rectangle approximations with n is equal to 4, which again are based on 80, 75, 70, and 65, again with base length of 5, one can find that this is approximately equal to 0.2629. And from these two, if you average them together, as we already know, is going to be a trapezoidal approximation with n is equal to 4, one can find that's going to be approximately equal to 0.2611. But that's not necessarily going to give us tremendous accuracy, so what we can do is we can switch to a midpoint approximation. So a midpoint approximation with 4 rectangles, if we use base points 62.5, 67.5, 72.5, and 77.5, you can find that's approximately equal to 0.2620. And then once you have your midpoint and your trapezoidal approximations, you can have 4 Simpson parabolic approximations, which, as you probably already know, is just going to be a weighted average with your midpoint weighted twice as heavily, or in some sense 2/3 as heavily, as your trapezoidal approximation. And one can find that's approximately equal to 0.2617, which one can verify that as n gets closer to infinity, because n is 4 is actually pretty small for a length of 20, but one can find that 0.2617 actually are the first 2 decimals of the exact representation. So the probability that it takes anywhere from 60 to 80 seconds in order to answer or understand 7 math problems is around 26%. So that's how we can use integrals and also area approximations to answer questions about probabilities of continuous random variables. I hope you enjoyed this video, and I'll see you in the next one. Take care.